Hey loyal fans, I've created a number of SolveSpace tutorials over the years, and I respond to user comments. So if this tutorial leaves anything out, or if you want to suggest a topic I haven't covered, just let me know in the comments. This is my latest SolveSpace project. It shows how to create this waterproof cup and lid. I recently added a protein powder to my diet, a powder that needs to be mixed with water. Originally, I would mix the powder in a waterproof shaker, then transfer into a cup, but I realized this was a perfect excuse to design a custom 3D printable cup that mixes and serves. I've created a web page with downloadable resources for this project, the SolveSpace source files, printable STL files, and detailed pictures. Link in the description. If you get stuck or need more detail, just visit my website. Before we get into the actual cup design, here's a short overview of SolveSpace itself. My earlier SolveSpace videos cover this in more depth, links in the description. But it can't hurt to spend a few minutes on the basics. Here's the SolveSpace editing window. The middle area is where you draw things. Remember that you draw in 2 dimensions on a plane. That's the plane. I'm kind of rotating it around. Right now we're in the XY plane. Imagine a tabletop with X extending to the left and right and Y extending near and far. Notice the purple window at the lower right. That's my key press tracker. It tells you which keys I'm pressing. It also shows mouse presses. The property browser at the right keeps track of groups you create. Right now we have just one group. The toolbar at the left has 3 main sections. The top section has drawing commands on lines, arcs, and so forth. The middle section has constraints, ways to control the drawing and specify lengths, that sort of thing. The bottom section has extrusion commands, how you create a 3-dimensional object from a 2-dimensional drawing. Remember about the toolbar that you can hover over a command to see what keyboard shortcut might exist. All the shortcut keys are shown in uppercase, but you don't need to press Shift unless that's stated explicitly, like this example. In this project, we sometimes want to draw in the YZ plane, which means we need to rotate the editing view to that plane and create a new group aligned with the desired plane. The easiest way to change planes is to mouse-click the desired plane and press Shift-W. Here we go. Press that plane, Shift-W. Notice how we're now in the YZ plane, and the blue arrow is pointed upward. After we've created the desired YZ group, it's a good idea to delete the original group to avoid confusion and redundancy. It's also a good idea to name the groups. In a large project, that avoids confusion, to have every group have a name. Remember for the future, to create a new drawing, press Shift-W to align with an existing drawing. For example, if I happen to be out of alignment, just press W and it brings the drawing into alignment. One more key idea. Well, let me draw some lines. To undo an action that you've taken, press Ctrl-Z. And to redo an action that's been taken that you've deleted, press Ctrl-Y. So Ctrl-Z deletes things that were, the actions that were taken, and Ctrl-Y recovers actions that you might have deleted in excess. See how all the lines are located on a plane? I'm rotating the plane, the drawing plane, To move on, I need to close the figure. SolveSpace drawings need to be closed, meaning having no gaps. Like a closed figure would be, for example, a cube or a square, a triangle, whatever, without any openings. Because this is an open drawing, SolveSpace rejects it. So let me close it. Okay, now that I have a closed drawing, I see that this drawing has 8 degrees of freedom. A degree of freedom is a fancy way of saying something that has been undefined, a length, an angle, or an anchoring point. So I need to provide 8 definitions to solve that and to go to 0 degrees of freedom, which is the desired outcome. So let's see, I think I'll make this a vertical line, specified as being vertical. So we have 7 degrees of freedom left. I'll make this one horizontal H, and this one H, and we have 5 degrees of freedom. Now we've specified orientations for these lines, but not their length. Let's try setting some lengths. And here the same. And this one. And we still have 2 degrees of freedom. I know what one of them is. I haven't specified where this object is located. See how I can move it around? So let me anchor it to the origin of the drawing, like this. We have no degrees of freedom, even though this line over here has no definitions attached to it. So let's say that I'm a student, I don't actually know how this works, and I know this line needs to be vertical. So let me just select the line and press V for vertical. Oh, I see we have something called a redundant constraint. A redundant constraint in a drawing means that there are more than enough definitions to fully define the drawing. Now first let me delete the redundant constraint and then explain. This line, which has no definitions attached to it, is fully defined by the other lines in the drawing. This line is 100 units long, millimeters long, as is this one and this one. This is vertical and these are horizontal. And what that means is this line is fully defined by the other lines. It doesn't need to have any explicit definitions of its own. Let's try setting a length, a diameter. And what happened was, instead of allowing the entry of a new dimension, it says 100 ref. This side's length has been fully defined by the other sides. There are occasions when you need to have a reference displayed, and that's how you get it. Anyway, fully defined. These drawings are all in 2 dimensions. To go to 3 dimensions from 2, we use extrusion commands, this group right here. Let me just choose one. Now I'm extruding my 2-dimensional drawing into 3 dimensions. And this new extrusion has 1 degree of freedom. And that degree of freedom is I haven't specified a depth. So let me just click this here and enter a dimension. Now, at this point, I have a 3-dimensional object based on a 2-dimensional drawing with all constraints eliminated. So that should serve as a proper introduction. Before getting into the main cup design, let's start with a relatively easy SolveSpace drawing, the waterproof cup lid. Okay, for the first drawing, I'm going to render the one of the cup lid designs, this one with 1 gasket. It's one of the simpler drawings, so I thought I'd start with that, sort of to break people in. And the first thing we need to do is choose the YZ plane, which I've just done. I want to delete this, which is not functioning and it could be confusing. So we have the YZ plane, which is desirable for 3D printing. And start drawing some lines. Three millimeters. Let's just zoom in. And now the long horizontal line, which I don't have to draw entirely, I'll just specify its length. This length is pretty critical because the cup lid has to fit snugly inside the cup, and the gaskets have to press against the inside of the cup's radius to secure a waterproof fit. So its dimension is pretty critical. And that brings us way out here. I'll bring this somewhere where I can see it, and bring this also somewhere where I can see it. Put it down here. Oh, I'll put it through here. Two millimeters on that one, and it needs to be horizontal. 6 millimeters there. And an angle of 120 degrees. And an arc right here. With a radius of 2 millimeters. Where are we at? Oh, duh. I've left out one. Now notice about the degrees of freedom that there are 0. Not done with the drawing yet, but it's a good sign that I'm keeping up with the requirements. I'm going to zoom in on this part. Now for the fun part. This is the part where I draw the overhanging grip on the lid. There's a command to force a rectilinear relationship between two sides, and the shortcut key is the left bracket, which it showed up here. Good, that's good. That'll allow you to keep track of of what I'm doing here. And for the moment, let's make this 10 millimeters. And I want this one to be the same as the base height of the entire assembly. And I want to share that. I don't want to have a bunch of floating definitions around that should be interdependent. And now for an arc. And a construction line. Another construction line. radius of 3. And now the fun part, a bit trickier. Okay, oh yes, one more arc. Now, notice how I have one more degree of freedom, and the reason for that is I haven't specified what angle this rim, this cup rim, handle rim, needs to be. And if I just grab these two, I'll move this one. Done. That didn't take very long at all. Clear some things up here. So they're easier to read. Remember about this dimension, the 42.250 millimeters. That's quite important. The two critical dimensions in this project are the cup's internal radius and this cap's external radius, this lid. We have 0 degrees of freedom, which means we can go ahead and create a solid representation. Ta-da! Now to go back to the original drawing. So I'm going to use this single gasket model as a template for the 2 gasket model by making some additions because I'm lazy. So this point right here contains a points coincident, which I'll remove, which allows me to slide this upward as far as I like and maintain the vertical orientation. And now I can add a few lines to add another gasket groove. Now let's see, I want that to be 2 millimeters. And I want that and those two to be the same. So I'll make them equal. I want these two to be the same. That to be horizontal for sure. And this angle here should be 120 degrees. And, well, we have a complete 2 gasket groove cap with only a few minutes of extra effort, and it's reflected in the output. We now have the rendering. In practice, of course, you would save this under 2 different names. You save the files under 2 different names and add these, make these additions to complete the second version of the cup lid. Oh, that wasn't so difficult. Now we start the main drawing, the cup body. This is a more complex design than in my past tutorials, because as time passes I've learned more efficient ways to use SolveSpace and exploit its more advanced features. One goal of this project is to explain how to create a reference diagram that controls the dimensions for the entire project. The other drawings rely on this reference to set sizes, which means you can change values in this reference diagram and the entire project is resized. Now we start the main drawing, the cup body, a more complex drawing with more groups. A group for the cup body, several for the handle, plus a special group whose purpose is to slice away part of the handle that would otherwise extend inside the cup. One purpose of this project is to show how to create a master dimension diagram that defines all the important dimensions for the entire project. The other groups rely on this master diagram to set sizes, which means you can change a single number in this master diagram and the entire project is resized. So let's start by creating the master diagram. This is the main dimension diagram. The first thing I do is, as before, I want the YZ axis. So again, the way you determine that you're in the YZ axis is this label right here that I'm pointing at, plus the blue arrow is pointing upward. Those are your clues. And in this diagram's sole purpose is to provide some dimensions for the rest of the drawing. And so what that means is the lines in this drawing are construction lines, which means they don't actually become part of a drawing. And these all need to be anchored. I'm keeping them as though they were normal lines until I'm ready to convert them all at once. Now this number, 44, is the inside radius of the cup itself. And this inside to outside is 4 millimeters. That's the thickness of the wall of the cup. And this line in the middle needs to be centered, so I'll press Y to center it between the two. I now have a redundant constraint, which I'll remove. And this height is 102 millimeters. And these two are equal. So Q for equal. And the middle line is going to be a top reference point for the handle. And I want that to be 72 millimeters. Okay, now I'll just select them all and make them all construction lines by pressing G. Okay, let's just separate these a little bit so they're easier to see. And I want to remove this unused group and set NURBS, force NURBS, which I won't try to explain what that's all about. And more experienced SolveSpace users say that that isn't necessary, but it always is. So, And also I'm going to give this a different name. I'm going to call it the dimension reference diagram. Okay, let's just look over the classic test. Oh yeah, also no degrees of freedom. So we know it's been corrected correctly. This again, this diagram is the reference diagram for the rest of the project, and it by itself it doesn't provide any drawing lines in the final product. All it does is specify dimensions. Okay, we're going to do the handle top sketch. And the handle top sketch needs to be positioned on a drawing plane that I specify by rotating this diagram with the top toward me. By the way, there's a way to get a perspective view of what's showing on the screen, and I've just turned that on so it's a little easier to figure out what's going on. And that key is the accent key to turn that feature on and off. This is orthographic, everything's straight lines, and this is perspective view. And you don't always want to have it turned on. It makes it easier to specify, to figure out where you're located. Now, if I select this point right here, that's the plane. I want to use that as a drawing plane, that point right there. So having selected that point, I now press Shift W, and I now have a drawing on that plane. I can prove that. See that? This new plane right here is the one I just created. See how it's lined up with that point? And so I'll just press W again to recenter. Oh, and now I definitely need to turn off the perspective. So I'm going to press the accent key again. Otherwise, it's going to be very confusing. W again. Left mouse, drag. So here we go. This is a construction line, and it's 12 millimeters long. And it is centered between the above and below of the horizon line. Not describing that very well. And the distance between here and here, oops. I want that to be 12 millimeters distant. Now one more line. This is construction, G, press G. .5 millimeters for a special reason that I'll explain later. Okay, now we're going to make a big oval. And an arc A, another arc, and this line and this line are the same length, so Q, same here, Q, and we still have 2 more undefined. That wasn't necessary. How about that? Okay, 0 degrees of freedom. Let's look closely at these dimensions. The center to center distance is the same as the construction line that defines things here. And it's 12.5 millimeters away. I'll explain why later. And it's 12 millimeters distant from the outer edge of the cup. This point here is the outer wall of the cup. This is the inner wall of the cup. And this is a reference line that I'll be using later on. I'll explain later why that's there. Okay, so that takes care of this drawing. And I need to give it a name. I think I'll call it Handle Top Sketch. Okay. Now, you're about to see what this was all about. Oh, let's use the perspective view again to make it more obvious what's going on. Now, what I want to do is take this drawing and extrude it in an arc like this to make the top of the handle. So I'm going to select this right here, and I'm going to select this option, and then the reason for that line should become obvious now. It's a way for me to specify an angle, which happens to be 180 degrees. So there's the top handle loop, if you will. In fact, that's what I'm going to call it. And because I specified all the dimensions in the drawing that led to it, it has 0 errors. And I just specified the only important dimension added to it, which is it sweeps through 180 degrees, a half of a circle. Now I'm going to make the vertical part of the handle. That ends up being pretty easy. First I go back here to the handle top sketch, and I select this line, and I press this linear and specify a height, which is 40 millimeters. And I'm going to call it Handle Vertical Extrude. Let's see what it looks like when tied up together. Now notice that I used the same reference diagram, the handle top sketch, for both this upper loop and the vertical extrude. I took advantage of the fact that the dimensions are appropriate for both. Now to create the bottom loop of the handle, like so. First I rotate the drawing, the view, and I select a point that's at the bottom of the vertical extent of the handle as a reference point. Shift W to create a new drawing, a couple of new lines that will be construction lines that are connected, that are anchored to points in the earlier drawing. That's important to emphasize. And G for construction. Okay, those are construction lines. Now a couple of arcs that are actually going to appear. Notice that all these elements are anchored to points in the earlier drawing. That's important to understand. Oh yeah. Okay, now just two arcs and two straight lines that are drawing lines, two construction lines, and we have 0 degrees of freedom. Now I'm just going to create the bottom arc in much the same way that I created the top arc. I'm going to choose these two lines and specify an angle of 180 degrees. And that's the handle. And I should call this I'm going to call this all this business about renaming is much more important in a drawing that is as complicated as this one. Okay, so that's a completed handle. Okay, now I know from past experience designing cups like this that this part of the handle here will extend inside the cup's radius if I don't do something about it. So what I'm going to do is create a drawing and an object that will slice away those parts and conceal them from the inside of the cup. Starting with creating a new drawing using that reference, which is the center of the drawing. Shift W, new drawing. Now an arc. Oops. Anchored here. And I want the extent of the arc to extend out to that center line in the reference diagram. Done. And a couple of more lines. And I want the angle to be, that's wider than it needs to be. I'll explain that it's to keep these lines from interfering with the reference diagram later in the construction. And in order to position this arc, I'm going to just use V for vertical. And I now have a fully defined arc. Now for the part where I have to select the vertical axis, which I have done, and this, and I'm going to specify the height in a way that I don't use very often. This yellow area that I'm highlighting right now is a plane component of the obscuring arc. I'm going to select this point right here and that. Now at the moment, this block that I've just created is part of the drawing. But if I select difference, these solid model operators using Boolean algebra can perform different activities. And if I select difference, the block disappears, but it also removes the parts of the handle that would otherwise extend inside the cup. I'm going to give all these pieces colors to make my point a little more clear. So let's see, let's start with the top loop. I'm going to give it a different color. And the vertical extrude. And the bottom loop. All the same color. Okay, and now my gadget that I just created, give it a different color. And the idea is that having done that, it shows where the interior clear object impinges on the handle and cuts away part of it. This makes it a little easier to see what's going on if I just align them. If I remove this, you can see how far the handle would have extended inside the cup. But with it present, it cuts away most of the handle. So the handle, which is a pretty good, nice looking handle, but it can't extend inside the cup. That would be very bad. So I would call that a success. This is one of the more esoteric parts of this project because it relies on Boolean algebra and one of the lesser used features of SolveSpace. Okay, somewhat anticlimactically, after the complexity of the handle part of the project, now I'm going to actually draw the body of the cup. So let me select this point right here and Shift W to get myself a fresh new drawing and draw some lines. An arc, whoops. With a radius of 4 millimeters. And what's this? And we want a reference line right here. To carry the wall radius over so that the floor radius will track it. Q. Now the floor radius, the wall radius will both be 4 millimeters. Okay, looks good. And let's make a body. Okay, that's phase one. Because of a subtle bug in SolveSpace, I can't create a curved surface right here. After several hours of trying, I was unable to do it. That has to be a separate drawing. So now we're going to do that. Okay. And just to make sure it's working, and we'll give that the same color as the rest of the body of the, make sure it's actually working here. Yes. Okay. I'm backing up a little bit. I didn't give this a name. Okay. Let's see what we have here. Yeah, looking good. Now, just for a demonstration, if I remove the interior clearing device and take a look at the result. See, here's where the handle would have gone through without the special step I took to clear out to lop off the interior of the handle. I suppose that's a bit subtle. But that's the finished cup right now. Okay, the cup is basically finished, but I have a gadget that I attach to most of my cup models to automatically measure their volume. I'm going to do that now. I also wanted to amend something I said earlier. I said I couldn't put a curved surface on the top of the edge of the cup. That's not quite correct. What I meant to say was that if I tried to resize the cup with a radius on the top edge, the model would disintegrate. And I was forced to divide the top edge of the top radius of the edge from the body of the cup in order for it to work properly and accept any size changes I cared to make to it. But right now, let's do the little volume the volume measuring device. Shift W and show all. Okay, that's the view I want right there. And an arc. The irony is that I can put arcs in some places but not others without triggering this bug. And oops, I just realized something, that this is one of the ways that I fixed this issue before. I need to have that be the vertical axis, otherwise it will also crash. But by the way, if you never change the size of the cup, these issues I'm describing won't come up. But I'm a perfectionist and I wanted to have the ability to adjust the cup size after the fact. So let's go ahead and create the measuring volume. And give this a proper name. Now, this will interfere with the drawing, so I click this option, suppress this group's solid model, because all this does is allow me to measure the radius, the volume. And during working on this project, that number, 594.108 centimeters cubed, is the outcome I expect. So if I'm feeling lazy and overlooking a lot of details, I get to this part of the project and I measure the volume, and if that number comes up, I'm reasonably sure I've got all the details sorted out. Anyway, these last two items, these last two groups, all they do is allow you to measure the volume, including the curve. By the way, this is obviously you can use some pretty trivial math for a cylinder, which we have the radius and the height. No big deal, right? But this, the volume of this object down here at the bottom, that's much more subtle. And so a while ago, while designing these cups, I got an attack of laziness and I worked out a way to measure the volume automatically. Because SolveSpace provides a volume measure if you give it a shape. Anyway, so that's the cup. And I can, and I might as well resize it since I went to all the trouble to make that possible. I just greatly increased the size of the cup. There you have it. And height as well. Height is easier for some reason. A kind of a ridiculous cup. I'm just showing off the ability of the model to, well, one, the fact that I have a single defining group that propagates all its own measurements throughout the project, and the fact that I solved some issues that prevented resizing from taking place. So now I can use this cup model for any number of applications where a different size is needed. So, finished cup, including a volume measurement. Let's just do that one more time. Yeah, that's the magic number. So that's our cup. This next phase designs a gasket for the waterproof cup. Unfortunately, my 3D printer, a Prusa Core 1, won't print soft TPU, which would be required to make my own gaskets. My printer can print hard TPU with a hardness specifier of 95A, but that's too inflexible for a gasket. So I acquired my gaskets from Amazon. Full details appear on this project's webpage, link in the description. This next design is an exact duplicate of the required gasket dimensions, so viewers may find it useful as a dimension reference while shopping, or to print if they have a printer able to print soft TPU. I did find a use for it as a model in my Blender animations. Okay, need a prototype gasket. I can't print it, but I have other uses for it. First, the obligatory switch of dimensions. Make sure that the blue Z arrow is pointed upward. Make these equal. And a construction line. And a couple of copies of that. Now, what I'd like is for this line to be exactly centered between here and here. And this line in much the same way on its own side. And this one as well. And these all have shared dimensions, explicitly called out dimensions, which I'd like to avoid. So let me say instead equal. And symmetrical. This is all about to make sense. Here we go. I'm now drawing the surfaces of the gasket. Yeah. Oh, I see I have some redundant dimensions here, which I'd like to eliminate those as much as possible. Make these three equal. So a minimum of called out dimensions and a maximum of shared dimensions. Okay, we have no errors, so I can now go and create a solid model. There's the gasket. That's all the phases for this project, and remember, I created a web page including project resources, link in the description. This turned out to be a much longer tutorial than my other SolveSpace videos, and it covers design methods viewers may find useful in their own projects. Thanks for watching. Please like and subscribe, and be well.